Hello, so this is a revision video for AP Chemistry 7.9, Introduction to Le Châtelier's Principle. Le Châtelier's principle states that when a system at equilibrium is stressed, it will shift to counteract the stress and restore equilibrium. What this means is when a system at equilibrium is subjected to a change in conditions, the system will shift in the direction of reaction that will reduce or offset that stress, eventually re-establishing equilibrium. So the forward or reverse reaction will be favoured until the stress is reduced and a new equilibrium is reached. Exam tip here, you may see Le Châtelier's principle written in different ways, but always avoid thinking of equilibrium systems as trying to do anything. Le Châtelier's principle is observational. It doesn't explain why such shifting occurs. The reason these shifts do occur is because the rate for one reaction direction increases or decreases more than the other direction, meaning for a short period of time, both reaction rates in the equilibrium mixture are no longer the same, so it doesn't remain at equilibrium. Equilibrium is broken. After a given amount of time, the rates will become the same again and a new equilibrium will be re-established. However, now the quantities of all species in the mixture will have changed, hence we describe the system as having shifted and the equilibrium position having moved. There are several changes in conditions or stresses that you need to be aware of for AP Chemistry. Effect of change in concentration. If the concentration of a reactant in an equilibrium mixture is increased, the equilibrium shifts to the right. More reactants get used up, and the product concentration therefore increases. Hence, equilibrium shifts to the right, favouring the forward direction. If, however, the concentration of products in the equilibrium mixture get increased, now equilibrium shifts to the left, meaning reactant concentration will increase and the product concentration will decrease. Reverse direction has been favoured. Note in both of these cases, the equilibrium constant Kc or Kp will remain unchanged. For example, for the equilibrium system A plus B going to form C, if more A gets added to the equilibrium system, equilibrium shifts to the right, which means more C will get produced and the concentration of A and B will decrease slightly until a new equilibrium system is established. Effect of change in temperature. If the temperature of an equilibrium system is increased, the endothermic direction will be favoured, and equilibrium will shift in that direction. Equally, if the temperature of the system is decreased, now the exothermic direction will be favoured and equilibrium will shift in that direction. For example, in the Haber process, the forward direction, so nitrogen plus hydrogen to ammonia, is exothermic. So if the temperature of the system is increased, equilibrium will shift to the left, favouring the endothermic direction, which would be the reverse direction. So the concentration of ammonia in the mixture will go down, but the concentrations of nitrogen and hydrogen will increase slightly until a new equilibrium is established. Note, however, that the value of Kc and Kp will change when the temperature is changed, because K, the equilibrium constant, is dependent on temperature. So in our Haber process example, because the forward direction is exothermic, increasing the temperature shifts equilibrium towards the reactants, so K would decrease, because the new equilibrium system will have a slightly higher proportion of reactants compared to products than before. Equally, because the endothermic direction is the reverse direction, if we increase the temperature, we shift the equilibrium towards the products, meaning K will now increase, because the new equilibrium mixture will contain a slightly higher proportion of products compared to reactants than before. Changing pressure for gaseous-based systems. If a gaseous-based equilibrium system has its pressure increased, the equilibrium will shift towards the side that produces the fewest moles of gas. Equally, decreasing the pressure will shift the equilibrium towards the side that produces the most moles of gas. If the moles of gas produced by both reactions are the same, changing the pressure will have no impact on the equilibrium position. Notice again that change in pressure will have no effect on the value of Kc or Kp, because only temperature changes the value of the equilibrium constant. For example, in the Haber process we've just looked at, there are 4 moles of gas on the left-hand side, the reactants, but 2 moles of gas on the right-hand side, the products. So if the pressure of the system is increased, the equilibrium position will shift to favour the direction that produces the fewest moles of gas. In this case, the forward direction, meaning the concentration of ammonia will increase slightly and the concentration of nitrogen and hydrogen will decrease slightly. Catalysts don't affect equilibrium position or equilibrium constants, K. The rates of the forward and reverse reactions are increased equally when a catalyst is added to the system. As a result, a catalyst simply helps a system reach equilibrium faster, but it doesn't affect the proportion of products to reactants in a mixture once equilibrium is reached.